And here we are once again. Welcome to the Physics 2A video lecture number 3. And I'm just going to pick up where we left off last time. So we were talking about dimensions and physics equations, straight lines, things like that. We were in a math review, and this is part of chapter 1. So let's just move on to the next example. I had given you a straight line, so just to keep some continuity here, we had a straight line, something you've certainly studied in algebra before, but for us it's already a physics equation in which the time is the independent variable and the position is the dependent variable, and we have the equation of a straight line, which is written x equals x0 plus b0t. The intercept, clearly x of 0, but these things have certain meaning. This is a position or a length. This here is a velocity. So its units are meters per second. Time has units seconds. Okay, so that's so much for review. I wanted to go to a parabola next. So this next example, y equals ax squared plus bx plus c. A, b, and c are constants. And if we were to graph this, y versus x, we could have any number of parabolas, right? Depending on the values of a, b, and c. I'll just do one like that. Okay, you've learned how to analyze those. So let's see what we would have in physics, and this example I'm about to give you will be coming up next week or the week after. Actually in chapter 3, so that would be a couple of lectures downstream from here. So what do we have that looks like this in physics? Okay, get ready. Y equals y sub 0 plus tangent theta x minus g x squared 2v0 squared cosine squared theta. Okay, in a few days I'm actually going to derive this expression for you, and we'll see its entire physics meaning. But right now I'm trying to show you something that is at first intimidating, but in principle is not, doesn't have to be intimidating. It's the kind of thing we have to get used to. So if we were to compare these two equations, you know, we'd see we've got a constant, so y sub 0 is a c. The b here is tangent of theta, and the a is minus g over 2v0 squared cosine squared theta. So those are coefficients that have all kinds of physical meaning, and what you do as you study physics, you learn to think of this thing just in the sense of this one, because this one you're not afraid of. This one is looking pretty impressive for the moment. Okay, let's go ahead and graph this. This is the equation of the path that, say, a baseball or a tennis ball takes when you throw it. So we have x and y. You notice this time it's not x and t, it's x here position. So this is actual the space of a plane. Y sub 0, we're going to do a launch and something comes up and falls down. Okay, you've seen that a million times. There's actually, I'll use a different color here. There's actually an angle involved. And just to make the comparison up here, so I'm going to write here, A is our minus G over 2v0 squared cosine squared theta. Our b is this tangent theta. And our c is this y sub 0. So that's when we're comparing these two expressions here. And I immediately have a great idea for a homework problem as well. Namely, so let's write homework here. Units of x and y are meters, which is to say x, the units of x are the meter, which we call one of these, lowercase m. Units of x and y are meters. Trig functions are dimensionless, have no units. B0, as we saw last time, has units of meters per second. So the homework is to find the units of g. Find units of g. Okay, and what you're going to do is remember, in this equation, everything is meters, 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 meters. Same thing down here. These are meters. This is dimensionless, so x is meters, but x is meters, therefore you have to square it. B0 is meters per second, so you have to square that. Trig function is dimensionless. Solve for g algebraically and then find the units by cancellation, just by analysis, the way we did last time. So this is a great problem. You'll find the units of g, and the thing is, this will only be an equation if the units are the same. So this is an important technique. As I introduce new quantities throughout the semester, we're always going to check out their dimension. And if you're ever analyzing an equation and the units don't match up, then you know there's a mistake in there somewhere. You got to go back and find it. So it's a very important technique. So this is a good homework problem. This will be due the end of the week of August 24th, along with these lecture notes. So that's a good start. So this is part of our math review. I have a couple more math review topics before we get to some actual physics demonstration. So I'll go ahead and erase this. Now I had done a little bit, written down some geometrical expressions, and I'm going to return to that. This time we're going to be looking at, here, call this geometry once again. So we have the volume, or let's start with the sphere. Its surface area is 4 pi radius squared, and its volume is 4/3 pi radius cubed. And I'll draw the sphere here just so we have what we're talking about. Radius r of the sphere. And now what we want to do, and there's a homework problem I'm going to assign at the end of the hour. We just want the ratio of its area divided by the volume. Now, why would we want something like this? This is an interesting example. I'll just put this as a note. The area, say you're talking about a human or an animal or some creature, then their strength corresponds to the area and their weight corresponds to their volume. Okay, the reason the strength corresponds to area is because it's the cross-sectional area of your muscles. Okay, so generally speaking, just in scaling terms, area divided by volume For an athlete, you could be thinking of strength divided by weight. Strength divided by weight. So I'll put this here as strength to weight ratio. So that's an example. But we're just going to go ahead and use our sphere. And so what we have is 4 pi radius squared divided by 4/3 pi radius cubed. And you'll see we get some nice cancellations here. 4 and pi. 3 comes back in the numerator. 3 divided by r. And then if we're just talking about proportionalities, we say that's proportional to 1 over r. So here's something you may not have ever considered before, but the strength to weight ratio, or that area to volume ratio, increases the smaller our object is. This is why small animals can just run up a tree, or you can drop a small animal from the top of a building, say a mouse, and nothing will happen to it. It has a higher strength to weight ratio. Galileo was a person who actually considered these things maybe for the first time. But anyway, kill 2 birds, 1 stone. So we've got an example here, strength to weight. And the homework problem is going to ask you something concrete about this as well. Now I've basically set it up for you. So this is in the denominator. The smaller something is here, right? Something's smaller than that ratio becomes larger because it's in the denominator. Good, so there will be a homework problem on that as well. And now I want to bring into play a little bit of trigonometry, just to remind you. And that'll roughly complete our mathematics review. These are the basic skills we need. You'll notice, I'll bring it up again, I'm not plugging in numbers, because the insights come from the algebraic expressions and their analysis. So, trigonometry is something we also have to know. Trigonometry. And I learned trigonometry just on the unit circle. Okay, so there's the circle x, y of radius 1. So we have x squared plus y squared equals 1. And then we go out here, and I'm going to use a different color. We have x and y written once again like that. And I'm going to put an angle in here. There's the unit circle. So we have our sine, cosine, and tangent. So we have sine of theta is simply equal to y in this case. Cosine of theta is equal to x. Tangent of theta is equal to sine. Cosine of theta is equal to y over x. Okay. Now, we then immediately have our sine squared plus cosine squared equals 1 identity. And if I just have a triangle in general here with the angle theta, I can also talk about the adjacent, the opposite side, and the hypotenuse. Okay. And under these circumstances, we have, say, cosine of theta is equal to the adjacent side over the hypotenuse, etc. We do sine and cosine, sine and tangent the same way. Why don't I go ahead and write them out? Sine theta is equal to opposite tan now, I want to apply these very basic definitions. And this next this next example is coming out of chapter 4 primarily. That's sort of a heads up and practice. So suppose we now have a ramp. I'm just going to draw a large wedge. Let's call this example inclined plane. Now, so I'll draw a large triangle here so we have something to work with and label. So this is a right triangle. Let's put an angle alpha down here. And this is the horizontal, so x and y, x is horizontal, y is vertical. Okay. Horizontal and vertical. And I could set up an inclined board here on my tabletop, for instance. Okay. Now, what we're going to do is place a little object here and extend a vector down. Did I say vector? We don't have vectors yet. We're just going to extend a line straight down in the vertical direction, and we're going to extend a short segment here, gotta make that a little neater, that is perpendicular to this inclined plane. Okay, so this is perpendicular. I want to extend this one here and this here so that I now have another right triangle. So let's make sure this looks reasonable. Okay. So let's just name this length here L. L is the length from here to here. What are these other two lengths? And what are the angles that we could label? Yet another color. So here's what we're going to do. By definition, this is a right angle. Okay. If this is an alpha, I'm going to name this thing beta. Okay. And immediately we see that, and because this is a right angle here, we immediately see that this little angle in here is the same alpha that we have over there. So we've constructed it. This is something we're often going to have to do. So if this is alpha and this is L, then, and I want you guys to do this and make sure you see it, because once you've copied it down, there it is. What you're going to find is this side is L sine alpha, and this side here is L cosine alpha. And this is a skill we have to learn. So we have to learn to set up triangles, right angles, surface normals as they're called, etc., and analyze them and identify them. Actually, I've done nothing but apply these definitions. So this is a very important example, and I'll just put here as a note, be able to do this. Be able to do what I just did. Namely, take it from the top, go around, find all the angles. In fact, this is beta right here. This is also beta, alpha, beta, 90 degrees, 90 degrees, 180 degrees, and so forth. Okay. So this is something you want to practice. I haven't brought this up yet, but physics is a subject, for those of you who've never had it before, that cannot simply be learned by watching. You can no more learn this subject by watching than we can go out to the track and watch the athletes and somehow get strong from it. Okay. We actually have to do this. That means, and that's of course why I'm having you do these lecture notes. as a very important part of the class. You have to do it. You have to do it a second and third time. Good. So that's the inclined plane example. And if you're able to construct this and then do your comparisons to make sure that all of these things are working out, we're very often going to take a triangle, a right triangle, and then figure out what, what the two sides are. Okay, good. Very important example. Yeah, so having this, I think we're ready to do some physics. Let me consult my, yeah, good. See how many minutes we have going on in here. Okay, perfect. We can do a little demonstration now. So our next topic is going to be in chapter 2. We're learning about motion. And before we just jump into the formal mathematics of it, I want to show a couple of demonstrations. And I believe that the camera will show the tabletop. Let's see here. So our topic is going to be falling motion. I better get this started here. Chapter 2, motion, falling, and free fall. I'll write those things down so we have the topics in view, and then we'll do a little demonstration. So chapter 2. Motion. So falling. What is falling motion? And then free fall. And then the nature of free fall. So here's a famous demonstration. Got something pretty visible. The famous hammer and the feather demo. And I usually do this in class and have them hit the floor, but not available to us right now. So we'll just have everything on the tabletop. So I drop the hammer and the feather at the same time. Which one lands first? No trick question here. I hope they're both visible. On your marks, get set. The hammer falls first. We don't need much more convincing. Okay. What about the feather and the tennis ball? On your marks, get set. Also the feather is slower, the tennis ball faster. So far, so good. I need a couple of other items here. Let's see if we've got, I have to sacrifice something here. We got this. Yeah, what I was looking for was some paper. So hammers, feathers, tennis balls. What about paper? Slower. If I were to erase the paper and the feather, now you could maybe start betting on this, right? About the same. Okay. Two more examples. The crumpled up piece of paper, loosely crumpled, too crumpled up, still falls pretty rapidly. So there are apparently many different forms of free fall, very crumpled up. And if you're wondering what's going on, or if it's on the tip of your tongue, or you already know, we're talking about the friction, we're talking about the air resistance, and the effect of the air resistance is to make everything fall differently. Now, there are actually videos of the astronauts on the moon doing this experiment in a lack of atmosphere, in a vacuum, and in fact, then the hammer and the feather fall at the same rate. Okay. Now you don't have to go all the way to outer space to do this demonstration. Here's another version of it. So the feather doesn't stick to the book at all. Okay, that's what I'm demonstrating right here. But if I put the feather on top of the book, tennis ball is good enough. Put the feather on top of the book and drop it, the feather fell exactly with the book. So we eliminated the friction of air resistance, and by eliminating that, we were able to make the feather fall as though it were in a vacuum. Okay? And therefore, it falls exactly like a rock or a hammer or anything else if you put it on the book. You can try this with something at home. It's a pretty interesting fact. Okay? Again, it's not sticking to the book whatsoever. It is simply falling in its nature with the book because there's no air resistance on acting on the feather. Okay, so it took people who thought about this longer than you'd think to come up with this, to really understand this. The significance of these demonstrations is that there is something called free fall, and that all objects fall the same in the absence of friction. And once that idea was there, we could then look for the law of free fall. Before that, everything fell differently. Leaves, rocks, hammers, you name it. And the ancients who thought about these things were not able to figure out that there was a true law of free fall for everything. Okay, so that's very significant demonstration for that reason. And I'll put a few words up there, and then we can start with the science of motion. Okay, good. Let me get rid of this. Yeah, that's a very important demonstration. You know, it's not always that you can demonstrate a law of nature like that as simply as eliminating the friction. So falling motion, things fall differently. Free fall, all, or actually what we'll do is we'll say fall without friction. So we've got falling motion, that's when things fall, no problem. Free fall is defined as fall without friction or with sufficiently little friction, okay? Negligible friction. So fall without friction for free fall, and then the law of free fall the first part of it is that all objects fall the same. Rocks, tennis balls, people, cats and dogs, everything. All objects fall the same. If friction is eliminated. Okay. And the second part of the law of free fall, its mathematical form, of the law. Well, that right now it's just a big question mark. We have to discover the mathematical form of the law, and then we'll have something. So, by the way, I'll just write here demonstration. Mind you guys, what we just saw. And what we'll do now is get into the necessary definitions of motion or the foundation of physics. So let's check the time once again. Okay, I think I'll go another 10 minutes or so. Good, okay. So what we're looking at is motion. And there is a set of concepts that I'll actually just list here, and then we're going to define them and do examples for them one by one. The concepts are position, displacement, velocity, and acceleration. If we get through those, we'll have the foundation of everything we're going to be doing. So position first. We're going to use the letter X for it. And X is a position. It has the dimensions of length or meters. Okay. Position. And what that is just the location on a number line. So I'll get a scale here, 0, 1, 2, 3, 4, 5. Oops, mine goes right here. And if this is X in meters, the position is just some location here. For example, where I put that red dot. That could be A. And then X, or X of A, would be, you guys look at it, 2.5 meters. And it doesn't have to be horizontal, it can be vertical, or I could define my position axis. Let's see what's a good way to go right here. To be along this incline, and then this would be 0, and this would be 1 meter in every place in between. Okay. So it can be any direction. It's just the location of something. So position or location. The next concept is displacement. We're going to call that delta x equals x final minus x initial, xb minus xa, x2 minus x1, call it a lot of things. That's the displacement, it's the difference. And if we do a number line for the displacement, zero, 1, 2, x in meters. So we have a number line for the displacement again, and I'll put, in fact, how about let's do b minus a. And then I'll locate these things at b and a. So say we started here and ended up here. Okay. Then in my example, delta x would be xb 1.5 meters minus 0.5 meters equals 1 meter. Okay, so that's the displacement, and we could have also started here at B and ended up at A. Had we done that, this answer would still be 1 meter, but it would have a minus sign in front of it. So the displacement can be positive or negative. So that's position and displacement. The units of displacement are clearly also meters. Dimension is a length, the units are meters. Good. So what's next in our list? Position, displacement, velocity. So velocity has some sub-definitions, but I'm going to keep it simple and just start with velocity v equals delta x over delta t. We already know what delta x is. That's a change in position, it's a displacement. Delta t is simply a time. Time or change in time, it really doesn't matter. I'm just doing this for the symmetric look of it for now. Delta x over delta t, so that's displacement over time. And let's make sure we see what the units are. We talked about these the other day. Delta x over delta t. The square bracket means we're just asking what the units are. So here we have meters, here we have seconds. So the velocity is meters per second. This also leads us to think about a definition in calculus where we could, instead of delta, we could say dx over dt. This is not actually a calculus-based course, but I know a lot of people have had calculus take the course. So that's the idea here as well. It could be a derivative, or it just could be a difference quotient. In either case, the units are meters per second, and displacement per time. Oh, let's give an example. The entire lecture hall that I'm in is 10 meters wide. If you're only seeing a few meters of it. How wide is this table, by the way? There's a meter stick, there's a second, and there's another half, a little less than half. Just under 2.5 meters. The entire lecture hall is 10 meters wide. And V could be 10 meters in 1 second, 10 meters per second. That would be a trivial example. Actually, what I wanted to write was V equals 100 meters in 10 seconds. Same quotient, but this may remind us of the 100-meter dash. The world record is somewhat under 10 seconds. So you immediately see that the fastest people in the world run at 10 meters per second. Okay. All right, for the 100-meter dash. Okay. So that's the definition of velocity, and we're very familiar with this. We always talk about miles per hour, for instance, when we're driving, and then that's a length over a time. Okay, so here we're just using meters per second. There's a meter, and a second is the time it takes to say 1001 to 1 second. Okay, what I want to do next, finally, I think I'll kind of end with this, is do an example where we construct a graph. First of all, we're going to take this equation, now take equation star, and cross multiply. I'm going to write solve for what do I get? X minus x0. That's my displacement, delta x, the difference, equals v times t minus t0. That's my delta t, right? And we're just going to simplify it by ignore the t sub 0. Then we're going to have x equals x0 plus v0t if v0 is equal to a constant. So what I've done, you see I've taken this definition here, velocity, and I've just derived that expression that we had analyzed on the board, the equation of the straight line. Okay? We had analyzed the equation of the straight line with exactly this equation. You see what I did to get there? This was an arbitrary thing anyway, and I'm going to go ahead and declare v to be a constant speed. So let me wrap this up by, well, I'll leave that. Wrap this up by redrawing that graph that we saw before and saying a little bit about it. And we'll save the acceleration for next time. Acceleration is a pretty big topic, and we need a little more time for it. So, carrying on with this, here we now have x, t, and I'll just title this x equals x0 plus b0t. Okay, here's my x0. And there's my equation of a line. Now, this is a point slope formula. This is the position at time equals 0. What does the slope mean in this picture here? V0 is the slope, and so you can see, let me label this 1, and I'll do a second line in the same graph. I'll label this 2. So between 1 and 2, who's moving faster? Who's moving faster? The greater slope, this has a greater slope 1 than this 2, and the greater slope corresponds to the greater speed, okay, or velocity. Slope, okay. Slope corresponds to slope corresponds to velocity. In this case, speed. Speed is the magnitude of the velocity. So technically speaking, we don't use them interchangeably. Sometimes we do. Okay. If it's steeper, it means it's going faster. Larger number there. Good. That's what we'll end with. And I'll just put a couple homework problems up. Thought I knew what I wanted you guys to do. See if I wrote it down. Yes, so homework problems. First one was the board problem at the beginning of this lecture with finding the units of G. And then also Chapter 1, problems, and these are all trig and dimensional analysis. The problems don't get into the motion yet. They're trigonometry, dimensional analysis, stuff like that. Problems, Chapter 1, 149 and 76. 149 and 76. Okay. So you get those, they'll be part of this set that you mail to me later in the week. I want to say one thing that I don't think I've mentioned yet. In my ordinary lectures, I usually take the beginning of the hour and spend time solving any homework problem at the board that anyone in the class wants me to solve. And I'm going to do that as well. If you email me with a request, and if it gets to my attention, I'll do that. Otherwise, I'll pick out problems that I think are important and typically work them on the board here at the beginning of each lecture. Okay, so that's something we want to get into once we have some stuff going on. Very important actually, because I want you to do the problems and then get the feedback on them. I'm not returning any graded homework to you. Okay, so that the feedback you get from me is if I do problems that were assigned at the board, and you can then look at yours and look at mine and compare. Okay. Good, so let's leave it at that. See you guys next time.